If you have ever looked at a physics problem and felt your brain freeze up, you are not alone. Imagine walking into a room and seeing this: weights spinning, blocks sliding, and springs bouncing, all at the exact same time. When you try to figure out how every single piece affects every other piece all at once, it is incredibly overwhelming. There are simply too many moving parts to track. Filmmakers actually have a clever trick for dealing with chaotic, busy scenes. They do not show you the entire set at once. They frame a close-up. In physics, we do the exact same thing. We call our close-up the system. It is the one specific piece we choose to look at. Everything else, the ropes, the floor, the surrounding air, gets cropped out of our frame. That is the environment. Solving even the most tangled motion problems begins with this kind of selective observation. Before we ever pick up a calculator, we have to decide exactly where our camera is going to point. Framing the right shot is so important that missing it stalled science for 2,000 years. The ancient Greek thinker Aristotle believed that if an object was moving, something had to be constantly pushing it to keep it going. It makes sense in our everyday life. If you stop pushing a toy car, it eventually stops rolling. But Aristotle was looking at the wide shot. He saw the car stop, but he failed to isolate the invisible force rubbing against the wheels: friction. Centuries later, Galileo zoomed in. He realized that if you could somehow remove that friction, a rolling object would just keep rolling forever. To a single object perfectly isolated from outside pushes or pulls, moving at a steady speed is exactly the same as sitting perfectly still. Everyday observations can trick us. To see how motion actually works, we have to intentionally crop out the noise and focus our lens on one specific subject. We can break this down into a 5-step production checklist. Step 1. Make a simple drawing of the whole scene. Step 2. Choose your star, the system. Step number 3. Draw a force diagram. Step 4. List the information you are still missing. And step 5. Apply the rules of motion to find the answer. Step 3 is where we create our focus. This force diagram is the most important shot you will set up in the entire process. This diagram strips away the physical object entirely. It leaves behind only a dot representing your system and arrows showing the pushes and pulls acting on it from the outside. You never include the forces your star is pushing back with. We only care about what the environment is doing to the system. Let's put this into practice. This setup shows a heavy block hanging from a ceiling by a rope. Right in the middle, someone pulls horizontally. To figure out what happens, we don't look at the whole room. Instead, we place our viewfinder over the central knot. That knot is our system. Everything else fades away. Now it is time to draw our force diagram. We replace the top rope pulling up and to the left with an arrow. We call that tension 1. We replace the person pulling to the side with a horizontal arrow. What about the heavy block? The block isn't our system. The knot is. The heavy block is just part of the environment pulling down on the knot through the bottom rope. So we draw a third arrow pointing straight down, which we will call tension 2. This clean diagram represents our final shot. The ropes, the ceiling, and the block are completely gone. We are left with a single dot and 3 simple arrows. By cropping our frame, a messy physical situation turns into a straightforward picture. Since the knot isn't moving, those 3 pulls perfectly balance each other out. Let's try one more. Imagine an iron cylinder resting on top of a wooden block. The floor underneath them is weak and it starts to give way. The block and the cylinder begin to sink downward together. This diagram shows our 2 falling objects. Where do we point our camera here? We could make just the cylinder our system or just the wooden block. But we have another option. Because they are moving downward together at the exact same rate, we can draw our frame around both of them at once. The cylinder and the block become one combined system. Drawing a wider frame like this simplifies things. The cylinder pushes down on the block, and the block pushes back on the cylinder. But those interactions stay inside our camera frame. They balance out, so we can leave them out of our drawing entirely. We only care about what the outside environment is doing to our combined block and cylinder system. Gravity pulls the whole weight downward. The yielding floor pushes back upward. To find out how hard the floor is pushing, we just subtract the upward push of the floor from the total downward pull of gravity. Because the floor is giving way, that downward pull is winning, causing our total mass to accelerate toward the ground. Look back at that intimidating machine from the very beginning. When you know how to frame your shots, it isn't scary anymore. Every spinning wheel and sliding weight is just a single dot with a few arrows pulling on it. This framing technique turns an overwhelming world into something manageable. By isolating one piece at a time, we make invisible forces visible and the complex solvable.